Hey guys, my name is Lily and my partners for this project are Caitlin and Logan. Today, we're going to be talking about how we did our project. We wanted to use simple pendulums, but we did that last semester, so we're going to spice it up. We used magnets to change the downward force on our mass. Let's figure it out.
Hello. So for the theory of our experiment, we can evaluate this force diagram. So we have three forces that are acting in the vertical position. So we have the force due to tension, which is coming from the string, which we kept at a constant length, but the tension itself will be changing throughout the experiment as we change the position of the magnet that's underneath the pendulum. And then we have two forces acting in the downward direction. And so we have the force due to gravity, which we know is a constant of 9.8 meters per second squared. But we also have the force due to the magnetic field. And this is going to be changing as we change the force, as we change the position of the magnet in comparison to the pendulum. As we are changing the force due to the magnetic field, we are changing the whole system. So for the second part of our theory, we can analyze this equation, which we will be using to examine our apparatus. So we have the equation T equals 2 pi times the square root of L over G, in which T is the period it takes for the pendulum swing, and that's in seconds. L is the length of the string, which we kept constant, and that's analyzed in meters. And then we have Q sub B, which comes from analyzing G. So G is the downward force that we have. Typically, it's just gravity, but because we're changing it due to the magnet, you have to account for that as well. So that's what Q sub B is. It's the force due to the magnetic field. So we can take this equation and we can solve for Q sub B, which is our missing variable that we have here. So in order to do that, we took the square root of both sides, and then we switched these, the numerator and the denominators of these, so that we have Q sub B plus 9.8 is equal to L over T over 2 pi squared. And then we subtracted the force due to gravity on each side, so that then we can have Q sub B is equal to the length of the string divided by the period over 2 pi squared minus force due to gravity of 9.8. And so then we can take this and plug it into our calculations to analyze our data.
Okay, for our methods, we set up this apparatus with our mass, our magnet, our protractor, and all of our assemblages for our structure. So basically, we pull the mass about 8 degrees for it to maintain the simple pendulum status. So we would pull it, let it go, start our timer, and let it swing for about 20 oscillations.
All right, guys. So it has come to that point in time where we're going to explain our calculations and our conclusions. So to do that, we're going to hop into the spreadsheet. All right, so here we are looking at our spreadsheet with our results from our experiments. As you can see, we first ran an experiment with no magnet and got our values for that. We ran 5 different trials for each experiment. So we got 1, 2, 3, 4, 5, 6, 7 different experiments. The 6 over here are experiments that we ran with varying distances of the magnet from the mass on the pendulum. So that is what this distance each is representing. So taking our results from all our trials and experiments, averaging them, and doing, the fancy math that we explained earlier, we end up with this graph that resembles an inverse square law, which is what we want to see. Inverse square law is something that is present in a lot of nature, and we can see that that is the case here. Slight percentage error of 26.3, but we've determined that that is acceptable. So possible sources of error include oscillations of the apparatus. That was something that happened in all our trials though, so we can count that as systematic error. And then also there's reaction time between starting and stopping of the timer, and also slight deviations between the angle between each trial. And then finally, we have our Coriolis effect. So all those errors sum up to produce our percent error, 26.3.
Hey guys, we're back at the Foucault pendulum here, and we want to observe how we can apply what we learned here in lab into the real life. So here we have the Foucault pendulum, which we can obviously see is a very large mass. And so because of its large mass, it would have eventually stopped at some point due to air resistance. However, because there is a magnet underneath the pendulum, it allows it to compensate for the air resistance and to continue swinging. In real life, we can use Foucault pendulums for navigation.
Aunque digan que soy un bandolero donde voy, le doy gracias a Dios